Hi everyone, this is Ramagiri Kiran, working as assistant professor in Department of Electronics and Communication Engineering at Marri Reddy Institute of Technology and Management, Dundigal, Hyderabad. Today we are going to discuss on the subject digital electronics. Course objectives of the digital electronics: number systems in logic circuits, basic techniques for the design of digital circuits and fundamental concepts used in the design of digital systems. Simple logic operations using combinational logic circuits and design of sequential logic circuits. Sequential circuit systems in terms of state machines. Concepts of programmable logic device. Course outcomes of the digital electronics are: after the completion of the digital electronics, students are able to learn CO1, understand the numerical information in digital forms, in different forms, and Boolean algebra theorems. CO2, implement the Boolean algebra and to minimize combinational functions. CO3, design small combinational circuits and to use standard combinational functions to build larger one, more complex circuits. CO4, implement small sequential circuits and devices to use standard sequential function blocks to build larger, more complex circuits. CO5, illustrate operation of programmable logic device and programmable logic arrays. Here the course of the syllabus of the digital electronics, it consists of 5 modules. First one is number systems and Boolean algebra. In second unit, it consists of minimization of Boolean functions and combinational logic circuits. Third unit, module circuits fundamentals, registers and counters. Fourth unit, sequential machines. Fifth unit, programmable logic device and threshold logic. Here are the references we are having for the digital electronics are R.P. Jain, Charles H. Roth, and A. Anand Kumar. First, Unit 1, Number Systems and Boolean Algebra. In this one, we are going to discuss on number systems. A number system is a way of representing numbers using a set of rules and symbols. A radix point is used to separate the integer part and the fractional part of the number system. Expression for this radix system is a of n minus 1 into a of n minus 2, so on to a1, a naught dot a minus 1, a minus 2, so on to a minus 1. Here n is nothing but an integer part, m is nothing but a fractional part. Dot is nothing but a represents a radix point. Example for radix point is 1101.01. 1101 is nothing but a, we'll call as an integer part. Dot 01 is nothing but a, we'll call as fractional part. The dot is nothing but a radix point. If you are having in decimal, if you are having in a decimal 26.18, 26 is nothing but a, we'll call as a integer part. 18 is nothing but a fractional part, which are used in decimal values. Radix or base, the number of symbols or values used in a number system is called a base or radix. Expression for this base or radix is 0 to r minus 1. where R is nothing but a base or radix. There are types of number systems. There are 4 types of number system. First one, decimal number system, binary number system, octal number system, hexadecimal number system. First one, decimal number system. Base value is 10. Base value is 10. Means 0 to r minus 1 is the expression, where r is nothing but a base or radix. 0 to 10 minus 1. 0 to 9, which displays up to 9 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which displays up to 0 to 9 digits. Example, the value of a decimal number is calculated by the sum of powers of 10. Example, 4, 5, 6, 2. We have taken an example 4. The decimal number is calculated in the sum of powers of 10. Means 10 power 0, 10 power 1, 10 square, 10 cube. Multiply them with 4 into 10 cube plus 5 into 10 square plus 6 into 10 power 1 plus 2 into 10 power 0. 4 into 10 cube. 10 cube is nothing but 1000. 4 into 1000 is nothing but 4000 plus 5 into 10 square. 10 square is nothing but 100. 5 into 100. 500 plus 6 into 10 power 0 is nothing but 10. 6 into 10 nothing but 60 plus 2 into 10 power 0 is nothing but 1 plus 2. By adding all these, we will get the 4562. That is the for decimal number system. Next, binary number system. The base value is 2. 0 to r minus 1 means 0 to 2 minus 1. We will get 0 to 1 means 0, 1. These are the digits of the binary number system. The value of a binary number system is calculated by the sum of powers of 2. 1, 0, 1, 1 is nothing but a binary value, which is calculated with the powers of 2. 2 power 0, 2 power 1, 2 square, 2 cube. Then multiply that one with 1 into 2 cube plus 0 into 2 square plus 1 into 2 power 1 plus 1 into 2 power 0. 1 into 2 cube is nothing but a, will get 8 plus 0 into anything will get the value 0 only, plus 1 into 2 power 1 is nothing but a 2 plus 1 into 2 power 0 is nothing but a, we'll get 2 power 0 1 means 1. 8, 9, 10, 11, you are getting the decimal value. Next topic, octal number system. Base is 8. 0 to r minus 1. 0 to 8 minus 1 means 0 to 7 digits you are getting, means 0, 1, 2, 3, 4, 5, 6, 7 digits you are getting. Okay, now the value of octal number system is calculated by the sum of powers of 8 means 236 in powers of 8. 8 power 0, 8 power 1, 8 power 2. 2 into 8 square plus 3 into 8 power 1 plus 6 into 8 power 0. 8 square, 64 into 2 we will get 128 plus 3 into 8 power 1, 8. 3 into 8, 24 plus 6 into 8 power 0 is nothing but a, you will get 1. 6 in 128 plus 24 plus 6, we will get the value 158. Next one, hexadecimal binary number system. Hexadecimal hexadecimal number system. Base is 16. 0 to r minus 1 means 0 to 16 minus 1 means 0 to 15. But in a hexadecimal, up to 0 to 9 it will displace. After that, a is nothing but a 10, b is 11, c is 12, d is 13, e is 14, f is 15. Example 2f3. It is calculated by powers of 16. 16 power 0, 16 power 1, 16 power 2. Is 2 into 16 square plus f into 16 power 1 plus 3 into 16 power 0. 2 into 16 square is nothing but 256. 256 into 2 is nothing but we'll get 512 plus f is nothing but we are having the decimal value 15. 15 into 16 we'll get 240 plus 3 into 16 power 0. 16 power 0 is nothing but we can write as 1. 3 into 1 we'll get 3. By adding 512 plus 240 plus 3 we'll get 755. Here I had given a table. Table represents 3-bit, decimal, octal and binary. Here decimal value 0, which we can written as 421, means all bits will get 0 only. When decimal value is 1, you will get the value will be 1 and the remaining bits will be 0. When decimal value is 2, you will get wherever the 2 is there, we'll get 1 and the remaining bits will get 0. 3, 1, 1, 0, 1, 1. 4, 1, the remaining bits will be 0. 5, 4 plus 1, 1, 1, 0. 6, 1, 1, 0. 7, 1, 1, 1, which will be represented as 111. And table represents 4-bit, decimal, hexadecimal and binary. 8421 you can write. When decimal value is 0, you will get the output all the variables zeros only. When decimal value is 1, when 1 is there, you will get the high value and the remaining bits will get 0. When decimal value is 2, keep the decimal value 2 value 1 and the remaining bits 0. 3, 0, 0, 1, 1. 4, 0, 1, 00. 5, 1, 1, remaining bits 0. 6, 0, 1, 1, 0. 7, 0, 111. 8, 1, 0, 0, 0. 9, 1, 0, 0, 1. 10. Here you can observe 10 value. In hexadecimal, it is represented as A. 1010 is represented in the binary. 11, it is represented in B. In hexadecimal, it is represented as B. 1011 is represented in binary. 12, in hexadecimal, it is represented as C. Binary values 1100. 13, hexadecimal is D value. 1101 is the binary number. 14 in hexadecimal, which is represented as E. 1110, which is represented in binary. 15 in hexadecimal, it can be written as F. 1111, which is represented in binary. Number system conversions. There are 12 types of conversions. First one is binary to octal conversions. binary to decimal conversion, binary to hexadecimal conversion, octal to binary conversion, octal to decimal conversion, octal to hexadecimal conversion, decimal to binary conversion, decimal to octal conversion, decimal to hexadecimal conversion, hexadecimal to binary conversion, hexadecimal to octal conversion, hexadecimal to decimal conversion. First one, binary octal conversion. Here steps are there to convert binary to octal. First step, start from the right. LSB. LSB is nothing but this one is nothing but a LSB, least significant bit. Least having the least value is nothing but a least weight, is nothing but we'll call as the least significant bit. MSB. MSB is nothing but a most significant bit which has the highest weight, is known as MSB, most significant bit. Group the bits in sets of 3. If left group has less than 3 bits, add leading zeros. Convert each 3-bit group to its octal equivalent. Example, 101101 to the base 2 is nothing but having a binary. Then split into 3 bits. 101 1 bit, 101 with another bit, which can be represented as 421 421. Add these two values, we'll get 5. Here also we'll get, add these two, we'll get 5. Nothing but a 5 to the base 8 is nothing but we'll get the octal value. Binary to decimal conversion. Steps to convert binary to decimal conversion. Assign powers of 2 starting from the rightmost bit, nothing but a 2 power 0. Multiply each bit by the powers of 2. Add all the values. Example, 11010 to the base 2. This is the binary number which we are converting into decimal value. 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. Here 0 is nothing but a LSB. Here 1 is nothing but a MSB. 1 into 2 power 4 plus 1 into 2 cube plus 0 into 2 square plus 1 into 2 power 1 plus 0 into 2 power 0. 1 into 2 power 4 is nothing but we can write as 16 plus 2 cube. 1 into 2 cube 8. 1 into 8 is nothing but we can write as 8 plus 0 into anything will get 0 only. 1 into 2 power 1. 2 power 1 is nothing but we can write as 2. 1 into 2 will get 2. 0 into anything will get 0 only. 16 plus 8 plus 0 plus 2 plus 0 will get the value 26 to the base 10. Base 10 is nothing but we will have a decimal. Next example, converting 11010.11 to the base 2. Here we are having two parts. First part is nothing but a integer part. Second one we are having a fractional part. First calculate the integer part. 11010 will get the value as 26 to the base 10. Okay, now fractional part. 11 means we can write as 2 power minus 1, 2 power minus 2, which can be written as 1 into 1 by 2 plus 1 into 1 by 2 power square equal to 1 by 2 plus 1 by 4, which can be written as 0.5 plus 1 by 4, which can be written as 0.25. By adding these two values, you will get 0.75. By adding 26.75 is nothing but a result of the 11010.11 is the final result is 26.75. Next one, binary to hexadecimal conversion. Start grouping from the right LSB into 4-bit groups. If the leftmost group has fewer than 4 bits, add leading zeros. Convert each 4-bit group into its hexa equivalent. Write the hexadecimal digits in the same order. First 1 1 1 1 4. From LSB group into 4 bits. These are nothing to 4 bits. Next here we are getting 4 bits. Next after that we are having no digits. Just add the zeros to that digits. 4 digits. Means here we are getting 8421. Means here we are getting the 3 value. All ones is nothing but a 15. 15 in hexadecimal you can write as F 001. Can write as 1. The total decimal value hexadecimal is 1F3 to the base 16. 110011 to the base 2 is nothing but we'll get the hexadecimal 1F3 to the base 16. Next one, octal to binary conversion. Take the octal number. Replace each octal digit with a 3-bit binary value. Write all binary groups together. Example 345 to the base 8. Convert 3 into binary 0 1 1 4 1 0 0 5 1 0 1. Then we'll get the final results of 345 to the base 8 is 0 1 1 1 0 0 1 0 1 to the base 2. Octal to binary conversion. Octal to binary conversion we'll get the final result. Just we have to group into 3 bits. By using 3 bits we'll get the value. 3 can be written in the binary 0 1 1. 4 we can write as 1 0 0. 5 in binary we can write as 1 0 1. Then we'll get the final results, which can be written as 0 1 1 0 0 1 0 1 to the base 2. Octal to decimal conversion. Base is 8. Digits we can use is 0 to 7. Each digit is multiplied by power of 8. 3 4 5 to the base 8. 8 power 0, 8 power 1, 8 square. It's nothing but a 3 into 8 square plus 3 into 8 power 1 plus 5 into 8 power 0. 3 into 8 square, 64 into 3 is nothing but we'll get the value 192. Plus 3 into 8 power 1 is nothing but we can write as 8. 8 3 is 32. Plus 5 into 8 power 0 we can write as 1 plus 5. 192 plus 32 plus 5 will get 229 to the base 10. 345 to the base 8 will get the final result is 229 to the base 10. Octal to hexadecimal conversion. Convert octal to binary. Each digit 3 bits. Group binary digits into 4-bit from right. Convert each 4-bit group into hexadecimal. Example is 56 to the base 8. Convert into hexadecimal 16. 5 value. First write down the 5 value in the binary 101 6 1 1 0. 56 to the base 8 can be written as 101 110. That is nothing but we are converted into binary. Then we have to convert that into hexadecimal, grouping into 4 bits. 0 1. Adding zeros, then we'll get the 4 digits. 1110 will get the value 8421 0010 2 H and then 14. 14 is nothing but we can write as E. 56 to the base H octal, which will get the value of hexadecimal is 2E to the base 16. References are, we are having the references Morris Mano, Thomas, RPJ, NPTEL courses also we can have digital circuits. Thank you.